Hello and welcome back to Maths with Mitch. Today we're going to be looking at trig graphs and their transformations. Particularly we're going to be looking at a formula and a general formula, as you can see there with those coefficients A, B, C and D. We're going to take each one in turn and talk about what difference they make to the graph and how you can transform it just by looking at those coefficients. Characteristic of the graph that we need to understand to be able to do this transformation is to know what the amplitude of the graph is. Now the amplitude is this. It is the vertical height from the midline of the graph. That is the amplitude. It's worth noting that it's from the midline. In this example, for y equals sine x, the midline is the x-axis. However, if the graph is vertically shifted, as we'll look at later, then that midline will change, and thus, for all the amplitude might not be different, the midline where it's measured from will be different. So when we're looking at y equals sine x, at the minute, y equals sine x, the term here, because there's nothing there, you could consider that to be 1, the number 1. So it's got an amplitude of 1. So if you were to change A, so let's say you were to change it to y equals 2 sine x, then your amplitude is going to be now 2. So whatever the graph now previously was, the amplitude is going to be twice as large. So it doesn't change the shape of the graph or the points at which it crosses the x-axis, but what we're going to have now is, rather than the peak being at 1, that peak's now going to be at 2. So the graph is going to follow the same shape, but peak at 2. And likewise, we said the amplitude was the distance from the midline. Therefore, the amplitude works the same in the negative. So on this side of the graph, this will also be the amplitude, and therefore that will also double to 2. So we can draw that, and that behavior will continue on both sides. So the amplitude, the coefficient written in front of sine x in this formula, changes the vertical height of the graph from the midline. Now for our second transformation, let's consider formula sine 3x. So our coefficient is now here. Let's call this b. But we're going to use 3 for the example. And now let's think about the effect that this has. Now for this one, we need to think about a term called the period. The period of a graph is the time it takes to do one complete cycle. Now you could measure that from the point at which it crosses here to where it crosses back, or a more common method is peak to peak. So you would measure from the peak to peak. That's the time it's taken to do a full cycle of the graph. So if we consider here, what is the period of y equals sine x? Here we've got pi equals a half. At this point here we have two and a half pi, or 5 over 2 pi, depending on how you want to write it. And so the period here is 2 pi. So it takes 2 pi for the sinusoidal wave pattern to do a full period. So for our example here, y equals sine 3x. For the period of any transformation, the shift is going to be 2 pi. You're going to divide that period by the coefficient b, which in our example is 3. So for us, we're going to do 2 pi divided by 3. And that will be our new period. for the graph. So when we do the shift, again we need to consider, in this instance, the period's the only thing that's changed. The amplitude hasn't changed, so it should still be the same height, but now your period is going to be 2 pi over 3. So rather than being 2 pi, it's now you're going to get 3 cycles in the same period because you've done divide by 3. So let's think about how that will look. The easiest way to consider it is you have 0 here. Now the first point at which it crosses is going to be pi. Instead, that'll now be pi over 3. So we're just doing this as sketch, but that'll be roughly here. So it'll be pi over 3. Then the next time it comes through is 2 pi for the normal sine graph. So that'll be 2 pi over 3, so 2/3 pi, or roughly here. And then the next time it'll cross is in another third of pi, so here. So now if we draw the graph with the new period, it will look like this, more rounded. And that will, my pen's gone haywire, but that will continue. So you could now continue to draw that at similar intervals here. But what we're now seeing is that the period here is now 2 pi over 3, as we can see. And the method for doing that, therefore, is take 2 pi, divide it by b, and that gives you the new period that you can then sketch. Hopefully a bit neater than I have, but I hope that gives you the idea. We'll add these all together at the end and we'll show you some combinations. So I will show you this again, but we'll move on to the third transformation. Transformation number 3. If we have something in the form of y equals sine, then a bracket with x plus, in this instance we're going to call it c. So our coefficient is now an addition to the x value. So what's that going to do? So what we need to now think about is the term a phase shift. So a phase shift is a shift or a literal move of the graph, and for this, when the coefficient is within the brackets with the x term, it is moving horizontally. So it's going to shift the entire graph in a horizontal direction dependent on what this term is. And this phase shift is horizontally to the left. So let's write that down. Phase shift left. And the amount it's going to move is dependent on the term c. So let's say we have the example y equals sine x plus, we're going to say pi over 2. I'm going to use pi over 2 because I'm going to make it nice and neat on my graph to be able to sketch it, but that could be a whole number, and you might have to consider what the numbers are rather than working in pi. But the concept is exactly the same. So we said it's a phase shift left, and this is a positive number, therefore it is moving to the left. So each point now is going to be pi over 2 to the left. So we can move this point, it's now going to be here. This point here is now here. This point here, again, move pi over half, and so on. We can move all the points. So now, when we join them up, we can sketch our new graph like so. The important thing to remember, it's a phase shift, but the graph is the same shape, same amplitude. The period, as we looked at just before, is the same, it's just moved to the left. So the entire line of the graph has moved in a phase shift, and in this instance by pi over 2. So you can see this point here where it was pi, it's now pi over 2. This point here, which was 0, is now minus pi over 2. So that's the third transformation, a phase shift horizontal. And our fourth transformation now is something in the form sine of x plus a coefficient d. So remember the big difference before, we had c was in a bracket with x, so you were applying sine to the entire function of x plus c. Now d is separate to the sine x function. So that's the big difference between c and d. But again, for this one, we're going to be looking at phase shifts. This time we're going to be looking in the vertical direction. So before it was horizontal, now vertical. So d is phase shift vertical. But it's the same concept as before, but just thinking about it in the different direction. The shape's the same, the period's the same, amplitude's the same. So let's do an example. Y equals sine x plus, we're just going to do 1. Keep it nice and simple. So again, we're going to apply the same method for when we sketched it. Pick a point, and it'll now move vertically up by 1. Okay, so this point here now becomes this point here, and we can replicate that for each point. And we can now join them up. So what you should see is the same shape of the graph, but every point on that graph should now be shifted up by 1 compared to its corresponding point on the other graph. Of course, if you had a steadier hand than me, it would look better, but what we're saying here is at each point here, it is plus 1. So phase shift vertically 1 by 1. Now a different way to look at it is to think of the midline before. So I mentioned midline when I talked about the amplitude. So it's easy for the graph of y equals sine x to say that the midline is the x-axis here. You can see that that cuts through the center of the graph. And in essence, when you're phase shifting, I did it with all the points because it's quite easy to plot that way. But what you're doing is shifting that midline up by 1. So if I can get a better straight line here. See that I haven't drawn the points on perfectly for this sketch, but you're shifting the midline up. So yes, all the points move, but your midline has shifted by 1, and that is the phase shift. So now, when we talked about amplitude, it's a lot easier to see that amplitude isn't the height from the x-axis here. It's the height from the midline. So you can see that both those have the same amplitude. So now let's consider a combination, and we'll talk it through with an example. So what happens when you've got multiple transformations happening on the same graph? So let's think about this. Let's do 3 sine x minus pi over 2 minus 1. Okay, so remembering what we had before, we said that this was A, B, C, and D. So we don't have a B term here. We said B was before the x. It was going to be something that times by whatever was in the X or in this bracket here. But we've got A, and we said A was a change to the amplitude. We don't have anything for B. We said C was a phase shift left. And D was a phase shift vertically, or up. So let's take each one in turn. So let's firstly look at the amplitude. We've got amplitude is 3. So what does that mean? We said that the amplitude was here from the midline. So that's going to be increased by 3. So now we're going to be at 3 at this point here. So this is a sketch, it's not going to be accurate, I'm a bit short on space here. These points are going to stay the same for the moment because they are the points at which it crosses, so their amplitude here is 0. This will be out to -3. And now we're going to just do it with a dotted line, because as we know we've got multiple things happening in this graph at once, but I want to do each one in turn and just show you what's going to happen, because this isn't the end result of the graph. But that is so far the impact of the 3. Now let's consider the phase shift left. Now we've written phase shift left, but that accounts for a plus C term. We've got a negative here, so that's going to mean it moves right. It's going to move right by pi over 2. So each one of these points here are now going to move to the right by pi over 2. So we can now replot those, remembering that we're talking about the green line now. And so we can now, let's do this in blue, and then we can see the effects. So now we're gonna add those effects up. So we've now got an amplitude of 3 and a phase shift to the left, which is actually a phase shift to the right because it's a negative. So that means our graph is now going to be here. Okay, so we now have done A, we've done C. Now let's think about D. That was a -1. I don't know where that's disappeared to. So -1, we said a phase shift up, or phase shift in the vertical direction is D. That was again plus D. So we've got a negative this time, so that's going to phase shift it down. So each point here that we had in blue previously is going to move down by 1. So this is going to move down here to -4. This to 2, and so on. So again, we can plot those and think about where they're going to be. Now let's, as I say, I find it easier to plot all the points, so we can do that there, move this down, that'll be there, this here, this. Said it was a sketch, but we'll join them up. But there we are. Now that is, all the blue lines have now shifted down, so that is the end result. So, you know, if you were doing this on a piece of paper with a pencil, you could rub out the previous sketches that you've done. You could do that step all in one if you could really visualize it very well. You could plot all the points, but that's step by step, talking through a summation of the different transformations that you might do on a sketch. So now let's look at that in review. So that was trig graphs and their transformations, and specifically looking at a formula in the form that you see on the screen there, and how we can do a sketch of the transformations to show how that graph's going to change. We did it for the sine graph. We could apply it to other trig graphs, but I hope that's helped. Thanks for watching, and please subscribe to the channels, and I'll be following with more videos. Thanks for watching.